In this video, we're going to learn about radians, which is another way to represent an angle besides degrees. Now, we're first going to start with an arc length formula before we get into how to convert between degrees and radians. Now, arc length is represented by S, which is the arc's length, is equal to the radius times the angle, which should be in radians. Now, what is a radian, you ask? Now, if you imagine that arc on a circle is equal to the radius, then that arc that is subtended by that angle is formed by an angle that is 1 radian. So it opens just wide enough so you create an arc length that is equal to the size of a radius, which is roughly around like 60-ish degrees. Now, how do we get this formula? Well, let's imagine two angles that are subtending arcs. And let's say we'll keep the green to be a general angle and arc. They both are bound to the same radius size circle. And we have another very specific angle and arc. But let's say the angle is 1 radian, then it follows that the arc should equal r itself. So if I follow through with this now becomes theta over 1, because it's 1 radian. I can plug in a value for it. And S over R. But when I multiply each side by R, I'll get the formula. S is equal to R times theta. So very easy to find this formula, and it's based off the definition of a radian. So for example, if I wanted to find the length of the arc of a circle of radius 2 meters subtended by a center angle of 0.5 radian, or a quarter of a radian, then first I need to point out that the radius is 2 meters, so R would equal 2. The angle is 0.25 radians. So theta will equal 0.25. And I just simply go ahead and plug these in. So it'll be 2 times 0.25, which when simplified gives me 0.5 meters, or half a meter. So not too complicated there. But now we can use this formula to create a conversion rate between degrees and radians. Because degrees have a unit, and radians, since it's more based off a distance, it's like an angle without units at all, which is very useful. Now let's say we let theta equal 1 full revolution, which tells us that the arc of that 1 full revolution would just be the circumference of that circle. So the arc would be just 2 pi r, that formula for the circumference of a circle. So I can change S to 2 pi r, and then I'll have r times that theta, which represents a full revolution. Now, I can divide each side by r, give me theta is equal to 2 pi. And this is radians. That angle is now equal to radians. Very nice. Now, we just talked about theta being equal to 1 revolution. So a full revolution is equal to 2 pi radians, which is that first conversion rate formula you want to keep in mind. If you ever hear of a full revolution, that's 2 pi radians. Now, 1 revolution in degrees is 360 degrees, which will be equal to 2 pi radians. If I divide each side by 2, I can get that 180 degrees is equal to 1 pi radians, which is another very good formula used for a conversion rate. Because now I can either look at the fact that 1 degree should equal pi over 180 radian. Or I can say that 1 radian is equal to 180 over pi degrees. which are two great formulas used for converting. So if I want to convert all these angles in degrees to radians, what I would have to do is change that degree symbol. I know that 1 degree is pi over 180 radian, which will give me 150 pi over 180, which can be simplified, that fraction, to 5 pi over 6. So you can say 150 degrees, or you can say 5 pi over 6 radians. Now, if it's a negative angle, still the same conversion rate. We have negative 45, and that 1 degree is pi over 180 radian, which gives me negative 45 pi over 180 radian, which can be simplified to simply negative pi over 4. And the same thing for 107, but this time I'm going to show you a slightly different way to represent your answer at the end, depending on what the context of your problem would be. So again, the degree can be changed to 180 radian to pi over 180 radian, but this time I'll get a fraction that cannot be reduced. So let's say I don't want to keep writing this over and over again. There's 107 pi over 180. The previous two were simpler to write, but this might be a pain to write over and over again. I can also just plug that into my calculator and get 1.868, and it's that many radians as a decimal. If you'd rather use the decimal, it depends on the situation. Now, let's say we have it in radians, but we want to convert it to degrees. Now, often we can visualize degrees a little bit better as an angle, so it might be good to know how to convert back into degrees if you're given a radian. So I have 3 pi over 2 radians, but now 1 radian is 180 over pi degrees. So I can take that radian, change it to 180 over pi, and now the pi's will cancel. I can do 180 divided by 2. And I'll get 3 times 90 degrees, which gives me 270 degrees. So 3 pi over 2 radians is the same thing as 270 degrees. Now, that same conversion method can be used for negative radian angles as well. Again, 1 radian is 180 over pi degrees. The pi's will cancel. 180 divided by 4 is 45, so I get negative 3 times 45 degrees, which gives me negative 135 degrees. Now, let's say we don't have a pi in our radian angle measure. Still the same method. We take that 3, and we're going to multiply it by 180 over pi degrees, which leaves me with 540 over pi degrees. And again, very similar to the previous example, this might be better left as a decimal than as a strange fraction. So we can write this as 171.887 degrees. Now, a quick rule of thumb in previous examples, or in future examples, I'll typically tell you how many decimals to round to, but if I ever don't give you that instruction, 3 decimal places is usually a safe bet. Now, you now know what a radian is, how to find arc length, and how to convert between degrees and radians. Now, while the usefulness of radians might not show itself in this lesson, they are very useful for a number of things in trigonometry.